All right, hello everyone. Uh, Good to be here. Good to see at least some icons of faces, people who are attending. Hope everyone's enjoyed the conference so far, and it's my pleasure today to talk to you about data science for collaborative cybersecurity. Let's jump right in. First, a little bit about myself. Again, Phillip Schafer. I'm the director of data science at IronNet. IronNet's a cybersecurity company. I've been here since 2018. It's been a wild ride, a kind of period of rapid growth from an early startup stage and through some rapid expansion that we're having right now. Yeah, and I'm excited to tell some of that story to you today. Previously, I was a data scientist at another startup in the DC area called Optoro. And prior to that, I did a PhD in physics at Penn State and worked on an area that most people don't usually associate with physics, which is speech recognition and kind of the intersection of that field with neuroscience. I live in Columbia, Maryland. And yeah, that's enough about me. You can see my LinkedIn URL on the lower right there, and happy to connect with you at some other time. So let's get into the interesting stuff. Let's talk about cybersecurity. And so, the purpose of this conference really is to talk about translation of ideas between executives and data science practitioners. And so I thought I'd start at the executive level, like at a high level, why do we care about cybersecurity? And fortunately, I think this is a really easy story to tell. For anyone who's been paying attention to the news in recent months and years, you see a lot of news, a lot of bad news about all the attacks that are being levied against US companies, US government agencies, foreign governments, foreign companies. And really what becomes clear for anyone who's paying attention is that there are a lot of vulnerabilities out there, and that we really need some fresh ideas to improve the way that we're defending ourselves against advanced nation state style actors. And so, getting into the executive vision for our company in particular, we have a particularly high profile executive on our team who is General Keith Alexander, who some of you may recognize as the former head of the NSA, the first commander of US Cyber Command, really a big name in cybersecurity. And so he founded IronNet with the vision that we can really change the way that companies defend themselves against these advanced cyber threats. So just looking at this quote here, imagine how much better our defenses would be if we defended as one unit instead of many individuals. A dozen analysts collaborating on a joint set of threats can be much more productive than a single analyst at a dozen companies working in isolation. And that is the true power of collective defense. And so really that is the high-level executive vision that we're trying to implement on our team as data scientists. How do we build the tools and the algorithms that are needed to allow companies to work together to defend themselves against cyber threats? And so as we start to think about how we implement this vision, the one thing that I want to convince you of is that this is essentially a data science problem, right? In order for us to see these cyber threats as they're happening and to catch them before bad things happen, we need to have visibility into what's happening on networks. And the way that we have visibility is through data collection, right? And so for us at IronNet, usually the starting place is we want to look at network traffic data. In a traditional kind of setting, we might go into a data center and we might install a physical sensor that's reading off packets from the wire, and we can extract metadata and use that metadata for detections. In other cases, increasingly customers are moving to the cloud and AWS and Azure and Google Cloud. And so we might be instead using log data that's either reflecting network traffic or activities of users on those platforms. In either case, we're starting with lots and lots of data, usually on the order of petabytes a day. And the first way in to finding the interesting stuff in that data is behavioral analytics. So behavioral analytics is a general term that we use for all sorts of algorithms that are going to find the needle in the haystack, look through all of that data and find the interesting things that are potentially suspicious or malicious that we can then put in front of an analyst or do remediation against. And so this is a big data science problem, is just finding those detections of things that are interesting or suspicious or anomalous in that large pile of data. And just to dive a layer deeper into this, the way that we build these behavioral analytics, we like to think about this problem being broken down into a cyber kill chain, right? So these are the stages of an attack that an attacker would go through, and if we can catch it at any of these stages, then we have a chance to stop what they're doing. And so what you see here is a listing of some examples of the behaviors that we try to target with some of our analytics. Starting on the left, reconnaissance, so an attacker's going in and scanning over ports and IPs, trying to get an idea of vulnerabilities in the network and find a way in. Access, looking for activity where a user clicks a phishing link and we can see that traffic on the wire, or someone is downloading a suspicious file that is potentially malware. We get into C2, which stands for command and control analytics, where malware has been implanted on the network and is communicating with a server outside the network that's controlled by the attacker. And we can see the traffic between those two entities and potentially detect the activity at that stage. And then finally, the action, right, which is the kind of, the attacker has an end goal, which is often to exfiltrate some data or whatever the case may be. We want to, if all else fails, catch things at the action phase. And so in each of these cases, we've designed analytics that can, through any number of methods, identify these particular types of behaviors. Sometimes it's heuristic algorithms, sometimes it's machine learning based, either unsupervised or supervised, depending on how much training data, labeled training data that we have in each case. And so I think that you would agree, looking at this, there's a lot of interesting data science to dive into here. And so this is a really exciting area for us. But I want to take it a step further, right? Because when you do those behavioral detections, you still have not yet reached that executive vision, right? Which is, how do we allow companies not only to find their own occurrences in their data, but how do we allow them to collaborate and to make sense of those in terms of a larger trend of what other companies are seeing, right? And so at IronNet, we have created this kind of unique architecture for allowing that interchange of ideas and information to happen. It's called Iron Dome. So the idea is we have multiple companies A, B, and C, which are all doing behavioral detection. And what the first step of this process is that they will just share that data out and into a common data store. And so, obviously, there are some concerns here about data privacy, and so we do a lot of scrubbing and minimization and kind of taking out any kind of proprietary information out of that data before it is shared. But the end result is that we get a single collection of potentially suspicious and malicious behavior across multiple companies. So these could be companies that are in the same geographical region, in the same sector or kind of commercial industry. And so we create these communities of companies and gather their data together. And then where the data science comes in is we want to take a look at all those events that are coming up into that data store and compute correlations. Correlations are just pairs of events that look like they could be similar. So in one example that we'll be running with through a lot of the rest of the talk, one of our command and control behaviors that we detect is DNS tunneling. It's a abuse of the DNS protocol where you can send data in and out of the network and communicate with an attacker. And so suppose that company A is seeing some DNS tunneling, company B is also seeing some DNS tunneling. We get both of those events in the same place and we say, hey, those look like they're similar. Then we can do this third part of the process, which is get those two companies into a conversation. They can share comments about those events as they do their process of triage and investigation. And then they can also share outcomes, like actual labels of malicious or suspicious or benign that they get to at the end of their investigation. And that will allow these companies to not just look within their own silo of what's happening in their network, but also see how it fits into a bigger picture. So this is the vision that we're trying to implement. Okay, so how do we find a correlation between events? In the early stages of this project, we took a very simple approach, which is just looking for exact matches between some of the fields in those two events. So for example, in this DNS tunneling case, if you have queries, DNS queries that are relating to a single app domain, your event 1 is DNS tunneling involving badguy.com. Event 2 is DNS tunneling involving badguy.com. Badguy.com is presumably a malicious domain controlled by an attacker. If we see both of those things, we can be pretty sure that, hey, you guys should talk. You're seeing the same thing, right? So this in itself is a great step forward. It's giving a broader context. It's giving you information that goes beyond the boundaries of your own network, but it's brittle, right? So in this cat and mouse game of detection and attack, the attackers always are looking for ways to get around your detection. So all they would have to do in this case is use a different domain, right? So it's the same attacker using even the same kind of malware, but they just swap out the domain from badguy.com to badguy.net in one of these networks. And suddenly we're not correlating that anymore. So what this shows is we need to have a more comprehensive view of what correlation is. How do we find similarity between these events based on a wider array of features and not just a single one? And so as we're thinking through this problem, we got very interested in the idea of metric learning. And so here I'm showing a diagram from a review paper from a few years ago, illustrating some of the concepts here. So in this case, the sample data set is images of faces. And in the initial feature embedding that you have for this data, you see that they're all kind of scrambled up and that there's not really any relationship of things that are close to each other in the space to the things that we would care about calling similar in kind of our view as humans looking at these faces, right? So what you can do is you go in and you turn this into a supervised learning problem. You put in some labels, okay? So here we'll go and we find some pairs of faces that look like they're the same person, all right? And that's shown with these green lines in here. And so those are labels and saying, we want these things to appear more similar to each other. And you also put in these negative labels, the red lines, saying here's some examples of faces that are not similar to each other that we want to move further away. That defines an objective function that you can optimize in any number of ways with a variety of machine learning algorithms. And you transform the space so that the things that you wanted to be similar end up closer together. And that's kind of the idea that we wanted to implement for this correlation problem. So we had some initial data I'm showing over on the right for DNS tunneling in particular, where we had samples of malware from different families. So there's these red dots are Alma malware, the green ones are WECB malware, the blue ones are some benign samples that we had. And you just do some PCA, and you can see there's already some kind of clustering here, but we'd like to group together those reds some more. We want to get a tighter cluster of green, and as we add in more labels and more malware families, we want to use this label data set to optimize a distance metric. And so just like walking through this story, like for our data science practitioners in the room, this will be a familiar first step. We need to get that feature representation that we can embed these events into. And it starts out for us with the picture on the left, which is a big JSON blob containing all of the behavioral information from our behavioral detection. So it's things like domains and IPs and byte counts and entropies and all sorts of statistics about the subdomains of the queries that we saw. And so we take that big giant dump of data and we run it through an internal Python package that we have that we call IronML tools. And that gives us out on the other end a bunch of engineered features. And we can easily configure this transformation to explore a lot of different ways of transforming that data. But we get some one-hot encoded features. We get some features that are scaled in various ways. So that's a very familiar first step of the process, is just getting a numeric representation of these events that we can apply machine learning methods to. Getting into the metric learning, right? So we saw the cartoon picture. We know we have an option to do supervised learning when we can provide those labels, those red and green lines in that picture that we saw. And so for example, for DNS tunneling, we had these malware families. There are other cases where it's harder to get labels. And so there are also a number of unsupervised learning methods that you can do. In either case, you want to optimize the distance metric that you're using for some use case. And so one kind of form of this that we zoomed in on was a weighted Euclidean, right? So you have two feature vectors. You want to say how similar or dissimilar they are. A Euclidean distance will give you some view of that. One step better is that you just add a weight to each term of that distance calculation. And that weight is kind of a feature importance. It tells you which of the features that you have is the most relevant to the similarity that you're looking for according to perhaps the labels in your supervised learning data set. And so over on the right here, you can see an example where we have run an algorithm. This one is due to Schultz and Jokins from a paper in 2003. You get out these feature importances, these weights, and some things are weighted more, some things are weighted less. It even eliminates some of those features. And what this gives you is a feature representation and a distance metric that is tuned to the problem that you're trying to solve and tuned to the type of similarity that you care about in your data. The next step is we have a way of saying that two things are similar, but how are we going to search through this massive amount of data, massive amount of events that are flowing into the data store to find those pairs that are similar, right? So you can imagine every single event that comes in, we want to compare it to all the previous events that we saw, right? But an n squared kind of a calculation like that is just computationally infeasible. That'd be way too many comparisons to make. So we use a technique called locality sensitive hashing to limit this down to a much smaller set of feature space in which we can do that search. And so the way that locality sensitive hashing works, so some of you are familiar with hashing. Usually the goal of hashing is to avoid collisions, right? So you start out with, up here on the upper left, the general hashing algorithm. You're trying to map these objects into hashes such that it's sort of pseudo-random, that you're very unlikely to have two objects that map into the same hash, right? Locality sensitive hashing flips that on its head, and it says that we actually want some collisions to happen, but we want the collisions to happen when those two things are close to each other in the space. And so the way that this works practically is, think about your data in some high dimensional space that we're representing as a cartoon below. You're going to choose some random vectors in that space to use for projections. So here we're choosing two of them, W1 and W2. And those two vectors that you choose slice and dice up the space into these smaller regions. And so, for example, looking at this pink dot here, the hash for that dot is 1, 2, right? So 1 along the, well, I guess it would be 2, 1 along the direction of W1, and then, or 2 along the direction of W1 and 1 along the direction of W2. So that pair of integers becomes your hash. And now if you want to find things that are similar to the pink dot, all you have to do is look at the other dots that are in that same bin, all the other dots that have the same hash value of 2, 1. So this is a way of very quickly narrowing down the search to a much more tractable subset of space where we can find the things that are similar. I'll just briefly touch on this. So we went through a process of evaluation with our Cyber Operations Center, our SIOC, where we said, all right, we have these set of distant metrics. We actually tried out several of them. You see 4 of them represented on this sheet here. And we wanted to get feedback, like, are the correlations that come out of this actually relevant to your process of triage and investigation of events, right? And so we went through a lot of historical data. We ran the correlations. We came up with these examples, and we put them in front of analysts, and we asked for feedback on whether these correlations look good or bad. And what you can see, briefly at a high level, for the ones that are labeled green, they're like, yes, these things are very closely related. So for example, we had a couple of events here, Banco del Rio and Banco Cilantro. These are both domains that were used in one of our red team exercises that we did internally. And so it's like there was the same guy running the same script, just with 2 separate domains. Boom, yes, we correlated those, and those were clearly related. And so we got lots of good feedback from our subject matter experts about where we did this right, where we did it wrong. And we were able to set a threshold for how similar things need to be to each other for us to call them correlated. And just to finish the story here, this has been a great success for our organization. So we actually have this running now in production settings. And we generate this kind of a report weekly for our customers, and it tells a story like this. We started out with 86 billion flows. That's that huge, massive data that we wanted to sort through and find the needle in the haystack. From that, we ran our behavioral analytics, and we were able to narrow that down to 216,000 events that we're actually calling alerts in this picture. We run this through a prioritization process to pull out some of the highest severity events that we had in there. And that gets us down to a much more manageable set of 675. And then by way of these behavioral correlations in our Iron Dome software, we're able to find 253 of those that have additional context from the community, right? Where we had either one or more different customers that saw the same behavior and that can then share ideas about that finding. And so, yeah, this has been a really fun area to work in. And it's really been exciting to see how we can translate that vision from General Alexander into concrete algorithms and data science practice. Finally, I just want to acknowledge a few colleagues and former colleagues who have been involved in this work. And I thank you for your time.